Good evening, everybody. My name is Moses. Welcome to my YouTube channel. Today, we are going to be having a simple kind of discussion, a simple kind of sharing in one of the topics that is solid state physics. So, we shall be talking about lattice vibrations, especially at different frequencies. So, with the word lattice, it tells us that there is somewhere. Okay, it's kind of a vibration that's so special. Sometimes we talk about vibrations, but then we don't know which kind of things vibrate. So we have got to think that even solids vibrate even when we don't know. So at this special occasion, we want first to understand what's the meaning of the word lattice. So we've seen that lattice is just a systematic arrangement. How are those atoms arranged within a solid? And what is holding the atoms? They have string-like structures. Some books also define them as strings, or they're actually springs. So by the time we have the concept of string and springs, then we realize that, oh, it means there is always an extension. So if there is an extension and we are seeing the word vibration, it means, hey, these things are simple harmonic. So how are we going to believe that even solids behave like systems that are of simple harmonic motion? That is what actually we are going to be seeing. So also we want to derive the fact that if these solids vibrate, then we want to relate what is the relationship between their frequency of vibration. If something is vibrating, then it has a frequency at which they vibrate. So what is the relationship between the frequency of vibration, and then there must be a constant of propagation. In vibrations, there is transfer of energy. So meaning something is being transported somewhere. That's why the concept of the constant of propagation comes in. And that is something we are going to cover today. And we'll be seeing it as we discuss on. Well, that is with that definition. So let's look at this structure that you just see about like the structure of a lattice, an example of a lattice. So when you look at this, is it two-dimensional, three-dimensional? So actually it's a two-dimensional. I'm seeing y and x axis, but how are we going to study something like this? This is actually graphene. This is the structure of a graphene lattice. How atoms are arranged in graphene. We see them, they are held by structures like strings, they look like springs at the same time. So that is how graphene is arranged. So that kind of arrangement is what we actually said is called lattice. Well, so what is so special with this lattice? We said one thing about lattice is, though we look at solids as they have structures holding them. Well, if they're being held and we have called them springs, then it means that they actually perform simple harmonic motion. That is one most important thing we have to consider. They perform simple harmonic motion. I think I need to note that down. We need to note that down, that they perform simple harmonic motion. So one of the x6 of lattice, it performs simple harmonic motion. So if it performs a simple harmonic motion, we know which equation can we look at? The most important thing we must not forget is this lattice must be also obeying the extension rule. Like extending, what comes to your mind when you talk about this extension rule? Like it must be able to expand. The extension cost is also proportional to the force you've applied on them. So that thing must be running in your mind. That's how they behave. You press them, that's how they also react to your pressing power or the external force you've given to them. And then the other thing, We also say the movement of atoms is shared by all atoms. Well, look at this closely. If I have this atom here, if it starts to move, it does not move alone. It's going to move based on the influence of other atoms. So they all move. That is so, so important, like not independent of each other. So if I have these atoms held together, well, if this one is going to move, then at the same time, we also expect this one to move. That's what happens. They all move. The motion is for all of them. One can't be moving and the others are standing. That's what happens with this kind of lattice that we're looking at, the lattice vibration. And then we also say that lattice vibrations may naturally occur due to internal energy or due to forced or external heat. It can be like compressions, like I can say, I have this pen. If I press it like this, I'm forcing those atoms to move, and at the same point, if I don't take care, I will most likely break it. So I will have broken some other law. Yes. So it can be either because of the internal energy, like it can vibrate due to its own energy, though I cannot see. But these things are fighting a lot of things. There are some conditions that are inside, but it has to make sure that the internal conditions are kept at equilibrium. So you find the atoms themselves can be vibrating about their mean positions. But the energy is not maximum enough to make it either break or heat up or something like that. So the vibrations can be due to that or forced, something like that, like external heat, compressions. And then we also say if it's not mechanical, that is involving this physical, we can also have these lattice vibrations due to electromagnetic radiations. We can project electromagnetic radiations into the solid, and then it makes atoms in the solid to start vibrating at different frequencies. So if it vibrates, there must be a frequency at which it vibrates. So if it vibrates, wow, if it already has frequency which is not fixed, but well, there may be a natural frequency if it's internal. That frequency is the one due to the internal forces, that it's trying to do its own work. What about if it's subjected to external forces? It might have another different frequency also. So if it has that kind of frequency that varies, then we also get to notice that these lattice vibrations, the atoms in lattice vibrations experience a wave kind of nature. They have a wave kind of nature. Wow, that sounds so sweet and nice. Now, finally, we are getting to understand the kind of nature of these atoms, and therefore we can study them properly. So if it's wave-like, simple harmonic, this is so sweet. So we can really get down and study them very well. So to get to this, let's dive into the main thing. We want to look at the one-dimensional lattice. Well, if you look at this structure, this is two-dimensional. We have y-axis, we have the x-axis. So it can be moving, it can be oscillating along the y and the x at the same time. So it gets so hard for us to study. So I want us to have a specific case. Let's say we are going to take vibrations either along the y-axis or along the x, or it can be along the z-axis if it's 3D. You know, we have x, y, and z axes, which we are familiar with. So let's look at a simple one-dimensional, and we are specifically going to consider the one along the x-axis for this case. So the monoatomic lattice. So from the word mono, this word itself tells you it's a one. It's a single atom. Why do we say single atom and yet we have different atoms where we see being indicated? Look at an example of a net. When you look at a net, a football net, those joints can be having some small balls which are called atoms. You could call them as atoms. That's the nature when it is shaking. So for us in this case, we are going to consider that all the shaking and the dancing of those nets, we have agreed that they dance together. It's not only one that vibrates. All of them vibrate, but we are going to look at specifically that the vibrations are going to be taking place along the x direction. So that is the most important thing we're going to look at. It's along the x direction. Now, if it's monoatomic, it means that we can study just one atom and then we are able to understand the behavior of the rest of them because they are similar. So one of the assumptions we are going to have is of all these atoms, they have the same mass. Let's call it mass m. Secondly, they are attached to each other by strings. We are going to neglect, in this case, the mass of the strings. Because they are not heavy, we are saying it's weightless. It's actually massless strings. Remember, we assumed because you can't even see these strings actually. When you study maybe so many things to do with string theory, you get down and discover so many hidden things. So in this case, we are just assuming that these things we are calling strings that are holding atoms together, they don't have mass. They are massless. So we are ignoring them. We are only considering that these atoms that are being held together, these ones here, as you see them, all of them have the same mass, and we've called that mass m in this case. So let's continue and see what best we can do about it. So if that is what happens, we are going to say that there exists interaction between only two nearest atoms. So what does that mean actually? If I have here these atoms interjoined like this, so this atom will have influence with this because of this nearest neighbor, and also have the impact from this nearest neighbor. That's actually what we're trying to say, that it interacts with only the nearest neighbors. And we also said, remember, it must be obeying the Hooke's law, which says that the extension that is going to be experienced on these strings must be proportional to the force you applied. If you apply more and more force, that's why if you heat and heat and heat solids, you realize that they melt because these strings can no longer hold them together. The shape actually gets lost. Yes, absolutely true. You can buy ice pack. It's rectangular, but because you're subjecting it to heat, you see it losing shape. It's gone because the strings can no longer hold those atoms together. So let's get back to this point. We are going to consider this monatomic lattice where we say the atoms have the same mass. Now, let's start the atom in position n. We can say the nth position. So an atom on the next can be n plus 1, n plus 2 going to the positive x direction. That's why we have these positions. N plus 1, we can have this th to show you the position. So the ones with the minus is actually showing you that it's on the negative x axis. So I was saying that these atoms happen to be obeying Newtonian mechanics. They also obey the Hooke's law, meaning extension is proportional to the applied force. Let's list some of the things. Also, the extension cost. In this case, I might have to use any letter. Let's use C in this case according to what we're using here. So it must obey Newtonian mechanics, the Hooke's law, and then also it behaves as a wave. It has a wave nature, so we should be able to get the solution of the wave. And we know if I have any wave, maybe if this is the displacement of that particular wave, it must be having this amplitude exponential. ik Na minus I omega t. Well, this is the constant of propagation. This is the frequency at which it's being propagated. Because if it's propagating, if it's being transmitted in some medium, then it means it has its own frequency. So our interest is to relate these two things, which is the dispersion relationship. Well, that takes us to have this idea that if this is the nth particle, then we have another particle, or we have another atom, which is in position n plus 1, the one on the right of it, which will be un plus 1. The only difference is this n. We shall be changing their positions. So, but the amplitude is going to be all the same. So we shall have ik n plus 1. And then the next one, n minus 1, will have the same amplitude, and this will be ik n minus 1. So what is this A? This is actually the interatomic separation. So what I mean by interatomic separation is this atom is separated from this atom by a distance A. That's interatomic separation. That's what we mean by that. So we are interested in finding the relationship between omega and the K, the constant of propagation. So when you look at this, it is actually what we're trying to do here, that the nth atom has this, and then we have the n plus 1 and n plus 2. Maybe we can have something like that. So this is something wrong. We are looking at one on the right, one on the left. So one is supposed to be, this is n minus 1, and this will be n plus 1, something like that. So one on the left and one on the right. So we'd actually have something, if you do this resolution very well, which I want us to try to do. So you will be having resolve this by putting back into the equation that we say these two things. Left hand side will have this, and the right hand side will have this. So this is left, this is right. So this x here is actually showing you this displacement, which we showed up here. These are the displacements, this part. So we want to substitute un plus 1, un minus 1. So that's why we are working for that. So when you look at that, you must be able to look at that the side that had minus m squared omega. Oh well, this omega, before we do that, we had d dt squared un actually. This part here is what gives us minus m omega squared. Because we are working on the left hand side of our equation, because remember we said according to this equation that we had right here, we want to get this left hand part, which is m du second derivative with respect to t, which is the Newtonian part. But the un is actually the displacement from the mean position of the nth atom. That's what we want to use to get for the rest. So that's what we're trying to calculate over here to get this. So we choose this red. So I have m omega squared. So how to get this omega squared? This omega, we said it has the wave nature. The atoms have that wave kind of nature. So the solution of a wave, we said if a wave for nth atom is u naught exponential ik na minus I omega t. So if we have this, then we need to differentiate it 2 times with respect to t for us to be able to get our left-hand part of the equation. That's why we have minus m omega squared for the left-hand part. So instead of us having this part, we shall be now having what we just got, minus m omega squared. So our task is now working on the right-hand side, which has, when we look at our right-hand side, we said it is c into 2un minus un plus 1. So we try to get the interaction, the force that is acting on the middle part, the middle atom, the central atom, and these neighboring atoms along the x-axis, the one on the left, one on the right, which is this expression. So we are interested in getting that force. So we want to substitute clearly into that expression. That what does it give us? This expression. After getting un plus 1, un minus 1, what then do you get? So it gives us our wave nature that we need to handle that part. So we shall have minus m omega squared equal to, if the constant we say is c, then we have c into e ika, and then minus 2 plus e minus ika. This is what we get. So we need to get some relation that connect these two things. This bracket, I see something to do with a sine and a cos, something like that. Some relationship. So if in case I need a sine of x, then I can say maybe e I x minus e minus ix. So divide by 2i, something like this. So I see some connection with this. So what did they do? Remember, our interest is we want to just get the dispersion relationship, omega, and the constant of propagation, a. What is our a? The constant k, I mean. What is then the a? The a is just the interatomic separation, which we looked at earlier. The distance between two neighboring atoms. This atom and this one, they are separated. They have an equal distance separating them. We call it a. So how are we going to relate this sin x and this expression we have? So you realize that it's connected to a sine squared x, which would give you minus a quarter into eix. If you look at this, I have minus e minus ix squared, all squared. That's what it would mean. Well, so instead of having this whole bracket thing, remember, this could be simplified dividing by a, divide by 2, divide by 2. Yes. So if you have that, it means that, let's have some other space for us. It means that I can have minus m omega squared equal to minus 4c into, well, minus 4c into sine squared ka over 2 if you divided them. So minus and minus is going away, omega squared, I can just go away straight away and divide all by 4c by m. I have sine squared ka over 2. So I need omega. So what do? You're going to take the root 4c over m, which would actually just mean that we are bringing out these 2. We can bring out 2 out so that I have c over omega. Let's not get stuck to these constants because this is a constant of propagation. Yeah, proportionality constant actually. This is a proportionality constant that we got using the Hooke's law that we related these waves to, these atoms to. So other books might use beta, other books might use a, something like that. So you don't have to fix yourself to this. So if you get the square root of this, we shall just have sine ka over 2. Now, this is our omega. This is just omega. But remember, it was a root, meaning we expect it to have two different values. So omega is either plus or minus of this. So at least we are getting some little light that omega has two values, and we are relating omega and k. And that was our goal. It's to relate k and omega. But still, we are not done. A sign, how does a sign vary? Our interest is to see this graphically. How is it going to work? So that's what we need to dive into. Like, we need to understand now, if we say really that these things are waves, then we need to understand that frequency at which they vibrate. Is the frequency low? Is the frequency high? Or actually at just a maximum frequency? There must be a maximum frequency beyond which, like, it's not possible for those atoms to even vibrate or to exist in that same state. So let's see what happens. So if we have it graphically, that we want to relate some values of the angular frequency and the constant of propagation, k. So we would have something like this. Now, how do we come to agree on such a graph? We need to observe the Brillouin zone condition. Actually, it's a k-space, coordinates along the k-space that don't go against the Bragg's line. Or if I have my coordinates from the origin, if I take coordinates from the origin, if I'm plotting my coordinates, they must not defy, or they must not go past or cross the Brillouin zone or the Bragg's line. So that's our main focus. So assuming we try to let's try checking maybe the second Brillouin zone by taking k, a k value that is, let's say, 2 pi. If you put 2 pi, we would actually not get what we need. Why? K plus 2 pi, like those maximum things, we would get solutions that are physical, that look physically identical. Well, it doesn't really make any meaning. So we are going to limit ourselves that let's look at the very first Brillouin zone, which has values of k. We want to set a standard for us to study. Let's have something that is quite constant. We want to set some small range. Now let's have k values that range from minus pi over a to minus pi to plus pi over a. Negative to positive. That's just along the Brillouin zone. So maybe this is what I would say. If I have a graph like this, I could have minus pi over a, I could have 2 pi over a minus, this is pi over a, this is 2 pi over a. These are values of k, and this is the angular frequency. Well, if I'm to plot, our values would be going like this. We would have graphs that fall out like this. At this point, this maximum point, it's where actually our first Brillouin zone falls, because we expected a relation that is quite linear. So at this point, there's a line that must not be crossed, called the Bragg's line. It must not be crossed. This is the maximum. So at this point, we believe this is the maximum frequency. So all points along the k space, the k coordinates, the k space, which don't cross that line, they fall under what we call the Brillouin zone. So this is our first. The next one, past this one, we have the second one, and we would continue to have them as many as possible. but we are limiting ourselves to only this. So meaning our study is going to be based on only this region. So let's look at the characteristics. Well, if we set ourselves that our K value must be from minus pi over A to positive pi over A, that must be the value of K, the constant of propagation. Well, that is what we have said. Now, what would the wave look like if it is moving at the highest frequency possible? So at the highest frequency possible, when do you think the frequency is possible? The maximum. It is at this. This is maximum. This point, it doesn't cross there. There is no any frequency that will propagate past that line. So if it goes past that, then it's actually going to the forbidden frequency. So it can't actually exist past that. It would be something else. So maximum frequency. What is that maximum frequency? When is the frequency called maximum? That's what we need to know. So we start first by looking at the expression we got. We said our omega must be, it's either plus or minus, meaning it has two coordinates, both on the left and the right, of it's twice C over M. I have sine K, A over 2. This is what we have. Well, so at maximum, when is omega maximum? Some books say frequency this maximum. It's all the same. When is it maximum? So it is maximum when this is 1. So which condition gives this to be 1? Meaning the whole of this, the whole K over 2, K over 2 must be equal to 1. So meaning K must be pi over A, which you have graphically here, that it must be pi over A. That must be the value of K for it to have a maximum value possible. So that's what happens at maximum frequency. So, well, that's not enough evidence for us to understand what happens to the wave at maximum frequency. We're still going on. If you have that, this has to be 1. So meaning the frequency is maximum at 2 C over M. I don't see anything left again. Well, there is something we need to understand. For us to conclude that this thing still moves like a wave, then it means, waves carry energy. Which kind of a wave is it? Is it one that is transferring energy, or it doesn't have any energy? So we've seen that at this maximum point, we don't see any other constant left. So if there is energy being carried, look at light. You have light moving. It's not just one photon. You study one photon, but it is a group of photons. It is actually so many photons in a line. So even these atoms, if they're transferring energy and really they're vibrating, then we expect them to be vibrating at a group velocity, which is the omega d K. Differentiate this maximum point. So what is the group velocity at a maximum angular frequency? If you see this, it's actually giving you 0. What comes to your mind? That if these waves are vibrating, if the atoms are vibrating at a maximum frequency, which is at when a constant of propagation, their constant of propagation is pi over A, then it means that the group velocity is 0. So if all the atoms we call vibrating and we expect to be transferring energy have 0 velocity, 0 group velocity, do you think they can transfer energy? Completely, there is no transfer of energy according to this. So what happens? They just appear to be standing waves. So standing waves cannot transfer momentum, they cannot transfer energy. That's what happens. If it's a standing wave, there is no transfer of energy. So we expect it to get some angular velocity, the group velocity, which we are not seeing. What about if we say, let's get the phase velocity, which is still omega over k. Based on what we see, we don't have the value of k. K is actually not seen anywhere. So if there is no k, then also it means phase group velocity, phase velocity are all zero. We don't have them. So, or rather, the phase velocity is something finite we can't define. We can't define, so we would not conclude that it's this, but it's a finite value, because if you know if omega is maximum divided by a value that's not there, we actually get an infinite value. So we can't tell actually the value of the phase velocity. That's what we see there. So the most important thing we're seeing that at maximum velocity, these atoms really can't transfer energy. So there is no possibility of transfer of energy. They stop propagating. That's what we would say. They just stay stationary. Amplitude is not changing, like it's just there, not moving. That's what happens at the highest frequency. Next, what about if the frequency is just high? Well, let's get back to our wave here. We expected this to be having a straight line, like we expected a linear kind of something, like linear dependence. That as k increases, we expect also the angular frequency to be increasing. But in this case, we want to see when the frequency is just high, not maximum, it's just high. So from our graphical representation here, we see at this point here, it's just high. It has not reached maximum, but it's just high. So it has ceased. It has stopped being linear, because if it was linear, it would go like that. So it's going to curve outwards. That's what we see at that point. So what would that signify? That at a high frequency, the light passes through medium, and then the refractive index now becomes a function of frequency. Like it now starts relating to frequency. So, and that's what we call dispersion. Like it's a phenomenon of dispersion, and then that medium that behaves like that becomes a dispersive medium. Well, at higher frequency, that you call higher frequency, if k is to increase, if we increase the angular, the constant of propagation, the angular frequency, initially, it increases as a straight line, like we can have this, that initially it will increase as a straight line at lower frequencies, but a point is going to reach when it stops being a linear function. Why? Because it's trying to attain now its maximum point at pi over a. So omega stops being a linear function of k. Doesn't stop behaving as linear. Initially, it was linear only at low frequency, but when the frequency becomes high enough, it starts curving. It stops being a linear function. That's what it's actually trying to show us there. And that is, if you look at it, we can do the mathematical expression. We do the differentiation as we say. That's basically that about high frequency.